We've talked about forces and net force and unbalanced force and so on up until this point over the last couple of days. Today I want to get a little bit more specific and talk about certain types of forces that make up the net force, that contribute to the total force. First one force that I want to talk about is the force that is commonly misunderstood, and that is weight. Your weight is a force. In fact, it is the force of gravity acting on you. Now, technically, that makes it a negative value, right? Because the force of gravity is a downward force, given that it is the mass times the acceleration due to gravity of negative 9.81. Think about that. If it wasn't a downward force, you wouldn't be pulled downward toward the Earth. Usually even though weight is technically a downward force or a negative force, usually we just make it positive, but technically it is a negative value. We're going to find it by multiplying m times a, but the a that we're going to use is the 9.81 a, the acceleration due to gravity. So what's my weight? Well, my mass is about 770 kilograms. So I'm going to multiply 70 kilograms. That's my mass. Mass, remember, is the amount of matter that I possess. It's the same everywhere in the universe. My mass is 70 kilograms on Earth. It's 70 kilograms on the moon. It's 70 kilograms in outer space, if I was to go to outer space. But my weight isn't. My weight is my mass times gravity, negative 9.81 meters per second squared. Or if I'm on the moon, it's 70 times negative 1.6. meters per second squared. 70 times negative 9.81, I believe, ends up being negative 6.9 times 10 to the 2 newtons. So I weigh almost 700 newtons. Now, when you think of your weight, you think of it in pounds, right? You step on a scale and it measures your weight in pounds. Well, the scale does, in fact, measure your weight in pounds. Pounds is the old unit for force, the imperial unit for force. Newton is the metric unit for force. So why is it that when I step on the scale, it says that I weigh 100 and whatever pounds or 70 kilograms? Well, I don't weigh 70 kilograms. That's not my weight. That's my mass. They're using two different things there, right? Pounds is weight because pounds is a measurement of force. Kilograms is not weight because it's not a measurement of force, it's a measurement of mass. In the end, okay, for most purposes, it doesn't really matter. But when we're talking in physics and we're solving problems in physics, it often does matter, the difference between weight and mass. Remember, mass is the amount of matter that you possess, and it's the same anywhere in the universe. 70 kilograms is 70 kilograms. Okay, weight is the force of gravity acting on something, and that's going to depend upon what the acceleration of gravity is. On Earth, about 9.81, although even that varies depending upon where you are on Earth, right? If you're in Vancouver, it might be 9.82. If you're at the top of Mount Everest, maybe it's 9.75. Okay, it does vary a little bit, but not dramatically. The further you are away from the center of the Earth, the weaker it is. Hey, weight. Normal force. Normal force is the force of the ground. I'm going to put that in quotation marks, and you'll see why in a second. The force of the ground pushing up in quotation marks at 90 degrees. The reason I put the ground in quotation marks is because it's not always the ground pushing up on an object at 90 degrees. Right now you're sitting in your seat. The normal force provided to you is actually being provided by the chair, by the desk, right? So in that case, it would be the force of the chair pushing up. Now, the normal force on the desk would be the ground pushing upwards, right? In your car, it's your car seat pushing upwards at 90 degrees, right? If you're on a roller coaster, it's the seat on the roller coaster pushing up at 90 degrees, right? The reason I put up at quotation marks is because it's not always pushing up either. If you're in your car, listen, if you're in your car, or you're just walking on the ground like this, horizontal ground like this, then the normal force will absolutely push up like this at 90 degrees. But if you're on a hill like this, the normal force pushes up, in quotation marks, at 90 degrees. See, this is a 90-degree angle, this is a 90-degree angle, but you can see that that upward force is not actually up, not actually straight up. End of November, beginning of December, when you guys go on your field trip to the amusement park, you're going to have to analyze a situation where the normal force is not going to be walking upside down. You're going to be upside down on a roller coaster loop sitting on the track or sitting on in the car, right? It's the car that's providing the normal force to you, the track that's providing the normal force to the roller coaster car. Which way is it acting? 90 degrees. So the normal force actually acts down there, not up. The reason we say up is because usually it is straight up, but understand that it doesn't have to be up. It's usually the ground, although it doesn't have to be the ground. It can be a seat, or it can be a car, or whatever it is it's pushing up. Now, what I'm about to say is really, really important. Okay, your weight is how heavy you are, right? It's the force of gravity acting down on you. But you know what? You don't feel your weight. How heavy do you feel right now? Okay. What do you weigh right now? What's your weight? Okay, so let's say 150, let's say. Okay? I weigh about 150, give or, well, I wouldn't say give or take, but probably a little bit more than 150, not much. Let's say you weigh the same, 150. Do you feel 150 pounds? Yeah, you do, right? But not because of gravity pulling down on you. You feel 150 pounds because the normal force pushes up. Think about that. You step off the edge of like maybe the first, when I was a kid, I remember as a kid, my elementary school, I grew up in Nova Scotia, you get way more snow, almost infinitely more snow than we get here. I remember one time actually, one snowstorm in the Maritimes getting 160 centimeters of snow. 160 centimeters of snow. Now, you don't have school for a week when that happens, right? But whenever we got lots of snow, my friends and I we'd go up to my elementary school. When I was in elementary school, I'd do this, and even when I was in junior high school, I'd go up to my elementary school, because my elementary school was a 3-story building. It was a 3-story brick building, and there was these wooden stairs that went up to the 3rd story. So you were at the top of the 2nd floor, right? You were on the 3rd floor, but 20 feet up into the air as you were on this wooden staircase, right? But sometimes the way the wind would come, you get 40 or 50 centimeters of snow, which was nothing. Like, that was common to get 40 centimeters of snow. And it would drift sometimes. So sometimes the snow pile against this was, like, sometimes it could be 2 meters high, like this snowdrift, not from being plowed, but just drifting 2 meters high. So we'd go up to this 20-foot high staircase, and then we'd jump off into the snow. And it never hurt, because we would jump into this soft snow. And it was great. We do that for hours. It was a blast. But as you're jumping, gravity's pulling you down, right? You're not weightless. You have weight because there's still a force of gravity acting on you. But as you're falling, you don't feel weight. You feel weightless. Why do you feel weightless? Because the ground's not pushing up on you anymore. You're only weightless when gravity disappears, but you feel weightless when the normal force disappears. So normal force is not your weight. Okay, that's weight. But the normal force is your apparent weight. This is how heavy you feel. Your perceived weight, how heavy you feel. Ever in an elevator? How many people have ever been in the CN Tower? Gone up the elevator in the CN Tower? Or like a really high building. I don't mean like a 4-story building with an elevator that goes really, really slow, but like a building that's 100 floors or something like that. Even a building downtown Calgary that might be 50 or 60 floors. Okay. When you step in that elevator, those elevators have to be pretty fast, right? Otherwise you end up being spending all your time in the elevator. Do you know that that's actually, engineering-wise, that's actually the single biggest impediment to tall buildings is elevators. We could build buildings way higher than we've built them, but we don't because of elevators. How do you get people up in an efficient way when the building is so high, right? It either takes so long or you have to have so many different elevators that the elevators take up the whole building. Okay, so that's actually a huge engineering problem, is building buildings high because of the amount of elevators that we need to keep people moving on those. Anyways, you get a really, really high building. You notice when you're in that elevator, you press the button for the 57th floor, and you're like, oh, your stomach feels like it goes into your legs. You feel really heavy there, don't you? You're not. You're same weight. If I weigh 700 newtons now, I weigh 700 newtons then, but I feel like I weigh 900 or 1,000 newtons. Why? Because the floor is pushing up on me harder. The normal force is what I perceive to be weight, and that's pushing harder on me. When I'm on a roller coaster going around a loop, I might feel 3 or 4 times heavier than I really am. I'm not, but because the track is pushing on me with a force of 2,100 newtons, I feel 3 times heavier than I really am. This is my apparent weight, my perceived weight. Does that make sense?